Ludovico, thank you very much for joining me today. I'm sure everybody's very interested in hearing your insights on the topics that we're discussing. The first question I've got for you, no problem. The first question I've got for you is, what areas within energy storage and renewables technology can you see having the biggest growth over the next 5 to 10 years?
It's a good question. I mean, I would say we can start with saying that nobody has the crystal ball, and that would be pretty obvious already. And everybody probably has different opinions, I would say. So this is my opinion, what I've been building my education on, what I've been listening and understanding around. And I pretty much agree that there is an undisputed exponential growth of battery energy storage systems, so the so-called BESS, that are becoming more and more embedded into our power grid. And that's kind of like stating the obvious, so I don't want to really discuss a lot about that specifically. But there is definitely a trend coming from the battery industry, which I'm pretty much involved into from a professional perspective, and which is also extremely interesting for all those people that are a bit skeptical, I would say, about batteries, which is sodium-ion batteries. I don't know if you ever heard of them, but they're becoming quite a big topic, because initially everybody has a lot of ideas and a lot of little concepts for new products, but this one is becoming pretty solid. And someone thought already this 2024 would have been a big year for sodium-ion batteries. And what is it consist on in pretty much? So like many of our listeners maybe might know, the standard main technology used for batteries is lithium, right? So you have different chemistries, different ways to do it, different specifications, but you're still pretty much bound to this metal, which is mined in a few locations around the globe. There are better ways to do it. There are very polluting ways to do it. There are expensive and cheap ways to do it, but it's not super abundant material if you don't want to find super expensive ways to extract it. So we just take it where there is a lot, pollutes a lot, and those mines are limited around our globe. So the point about sodium is that sodium is one of the most abundant elements of the Earth's crust. And once you are, let's say, breaking the boundaries of batteries that can be made with materials that are found around, pretty much digging a hole in your backyard, and you make a battery made of dirt, it starts to become cheap as dirt. It starts to become recyclable, and pretty much it comes from the ground. So you can, I wouldn't say dump it there, but that's pretty much the end of the recycling line. So imagine that you start building a battery with materials that are more and more recyclable, and they are cheaper and abundant, and everybody has them. I mean, what else can you ask from batteries, right? So, and how do we stand here? Is it a complete new concept? No, it's not actually. So there are proof of concept. There are prototypes, companies that are the big ones. So CATL from China, of course, is on the forefront in this. They have proven to have working prototypes. And by that, we mean that we can reach probably something around 80% of what the energy content of standard NMC or LFP lithium-ion batteries can provide. And in terms of lifetime, which is, of course, the other side of the coin, we are reaching something that is in the range of like 60% of the cycle life. 60 to 70%. And we could argue that in some of today's applications, you don't really need that super high energy density and super long lifetime that you can achieve with, NMC graphite. It's, imagine that you want to connect big containers or big battery systems to the grid. You probably don't have a problem with footprint. You can have personnel going and do maintenance there periodically. So it's not a huge problem that you need to put a battery on a satellite and leave it there for decades. You can maintain it. Then the problem becomes recyclability and cost and accessibility. And I think with sodium-ion batteries, we are really going to change something about this world. So I'm very looking forward to that. Another really interesting areas of development, which is not completely, or at least not as new as sodium-ion batteries, I would say, is HVDC. HVDC, also called high voltage DC. It's a waveform transmission of electrical power along very long distances, and also in a cheaper way. because the different, I don't know if you know, but I will try to get a bit more into the details here without boring too much the people. HVDC means that normally, let's start from the basic. Normally, when you transfer power from point A to point B, you're doing with AC because generation is done with rotating machines. So the easiest way to do it is in AC. Then you have transformers which use AC to step up, transform the voltage, and then you have high voltage line, which is necessary to run long distances. Otherwise, you will lose all your power very fast. So you need high voltage. However, AC, which was invented by Tesla in opposition to Edison back then, and he won the race because we are using AC. DC has a lot of advantages, and pretty much it means that you can put cables now subsea on the ground. You don't have to keep them above, these overhead lines on the highway. They are always big constructions. You need to keep cables far from the ground because you have impedance issues that are coming that prevents you from transferring a lot of power. Then you have so-called skin effect. So you're basically not using completely your cross section of the cable. Imagine that you put a cable that is thick like this, and then you're just using pretty much the surface of the cable. But there is no current really flowing through the whole section of the cable in AC. You're just using the surface because of physical reasons that I'm not getting into. But with DC, you're immediately using the full cross section. Also, you don't have reactive power with DC. So there are so many advantages. So the question becomes, why didn't we do it so far? Well, because there are certain engineering challenges in doing that. They are not a joke. The first one is that we need AC to step up the voltage. So then we do still that in the same way, and then we rectify the power and we make it run through long overhead lines. The next problem is safety. DC, and I think there were some funny examples in the past, but DC is extremely dangerous compared to AC because or at least it's more dangerous compared to AC because it's difficult to interrupt faults. Like imagine you have a big short circuit, you have an arc that is discharging megawatts of power from an overhead line towards a tree or something, and you're creating this fault to ground case, and then you have a part of your country that is without power. So normally what happens is that you cut that branch of the network to save the rest. Then with DC, that is extremely difficult. So the current keeps flowing. You need equipment that doesn't really exist yet. So it's, let's say, the safety aspects of HVDC that is the major challenge that we are facing now. But looking at what actually has been done. So we are talking about a pretty concrete technology that exists. There was one of the most recent projects is a project that is transferring 3 gigawatts of power from a wind park. I think it's in between New Mexico and Arizona. It's done at 500 kilovolts, and it runs for 800 kilometers. It's an extremely long distance. And this enables you to produce power in places where you don't really need it. And then you transfer a huge amount of power in cables that can be built underground, for example, so you don't have the overhead lines. So this is enabling an interconnection on a high scale that will allow you to produce power where it's convenient and transport it very, very far and interconnect countries where you have a lot of nuclear in one country, where you have a lot of wind in another country like Denmark. And then those countries, when there is no wind, you can use nuclear, but normally they're far. So it's very difficult to interchange power. And one last trend that I am really fond of, because I'm actually working with them, it's data centers. And you might say, why data centers? That's AI, that's stuff that is related to computer. How is that has to do with energy and renewable energy especially? And the point is that since we started using our dear ChatGPT or all these like AI tools that now are popping up every second day, you need to know that the energy that is used by these models, it's insane compared to what we were used before. Which is the main challenge to the potential growth of this technology, by the way. But consider that one query on ChatGPT requires 10 times the energy that a query on Google requires, 10 times. So use Google when you can, use ChatGPT when you have to, I would say generally. But also imagine these amounts, these like massive facilities that are burning energy. They will have to start becoming more environmentally friendly because that's a general trend that we need to do. They have challenges in connecting with the grid, so they will start having battery energy storage. They will start having ways to do backup with fuel cells. They will have pretty smart energy and power source redundancy architecture that at that point they become pretty much energy assets that are connected to the grid that you can use for other uses. You have massive amount of batteries that you can do energy arbitrage with, or you can do frequency regulation with. You have fuel cells, and whenever you don't have to use it as a backup for the data center, you can use it to provide power to the grid. You can do grid storage. And another funny thing is that once you connect all these data centers, because that's the whole point, it's like it's IT, it's stuff that is interconnected. You move data from one point to another. One thing that they're already doing, Google especially, I think, which is one of the main hyperscalers of these AI data centers, they are capable nowadays of moving loads, IT loads, from one data center to another around the globe, depending on which side of the globe is in that moment hit by the sun, because you have a lot of sun power that sometimes is not even used, right? So you move the load from the US to somewhere else just because the US is in the dark. And then you can enable this, becomes a major network of energy facilities that are highly interconnected.
Yeah, amazing. I think, all three sound exciting, and I think, the underlying message I got from all of that is that, these new technologies, they may require compromise, but ultimately it's in aid of sustainability, isn't it? And, in aid of creating a better environment for all. And I think that's ultimately why the compromise is probably necessary and something we should push for.
Absolutely. I think technology creates challenges sometimes, but also presents a solution for that new challenge. And then you have a new problem and you find a new challenge and you hope that at least there is an improvement over the time, right?
Yeah, definitely. Okay, so question 2 is, what's one piece of advice that you were given that you feel has had the most impact on your career?
So it's actually something that sometimes I pull out and I try to use it as a quote, because it's not really like an advice. It's more like, it's literally a quote. So a senior colleague of mine, an engineer back in my previous job, I used to work with GE, and he was a very admired colleague also for his simplicity, like no fancy words, just straight content. And I remember him for something that happened probably like 6 years ago at least. We were in a meeting and somebody asked, because, and all the engineers that might listen to this, they probably find themselves and they recognize themselves in this situation, because engineers many times they get asked by whoever, their managers or other non-engineering people, like, can you do this, or like, can we do this? This is a very common question, I assure you. Like, engineers get that a lot because it's partially their job to make stuff and to make stuff possible. So I don't know, John, can you do this? Can you do that? And this guy replied, well, everything can be done. Look back. Like, we went to the moon 50 years ago. We built AI now. What is impossible to do? We fly, 100 years now with the airplanes. What man can't do? And the real question is, what is worth doing? And that's something that I think people don't ask themselves a lot, because whenever you see like unsuccessful businesses, it's because they get stuck with like maybe processes that they don't have the capacity to deal with, or because they lose a bit the understanding of what is their mission and what is worth really doing. Everybody tries to do everything because they get caught by FOMO and they see the competition, and that works outside in the market as well as inside into a company. You try to copy processes that another department has done without maybe sometimes remembering what is really your mission and what is really like you're trying to do. And engineers, that's like a gold mine. Once you ask to an engineer, what can you do? Like, that's, I mean, everything really like becomes almost a challenge, an intellectual goal to try to make the most complex thing ever. And the question really, like, you should always ask yourself is, what is worth doing? Because we spend a lot of resources, and I talk by experience in a couple of jobs that I had. There is so much work that is done that is not needed to be done. And it's all about efficiency in the end. It's a word that is running by effectiveness and efficiency. I always say they are different, right? I live in Germany. They say Germans are efficient, and I always say no, Germans are effective. They're not efficient. There's very few things that are efficient in the German society nowadays. Efficient means basically receiving an okay result with a very low amount of resources. Effectiveness means reaching 100% of the result, regardless of how many resources you have. And that's something that is not sustainable. Like from a corporate but scale-up perspective, you can't afford putting resources in something that is not worth it. So, and that's also something that maybe people are scared of to say to their manager whenever they get asked, "Can you do this?" And then maybe the employee replies, "Okay, but why should I do that?" Right? And this is actually very healthy, I think. And I try to enable that in my team, and I try to be, I wouldn't say an ambassador, but I try to repeat this to other colleagues of mine, to my manager as well. I try to ask why. And you should be able to ask why 3 or 4 times, and the person that is giving you a task or is telling you to do something should be able to answer that. So like deeper and deeper and deeper, like a child. No? Why are we going there? You would give an answer, and then it finds another loophole, another hole, and ask you why. If you can't give an answer 3 times why, you haven't understood the task yourself.
Yeah,
that's the whole point. So how can we be successful in a world where competition is really becoming more and more tough out there, especially whoever wants to jump into the energy storage business? You know, I started doing this job. I work with energy storage systems for the past 5 years, and now I would say that pretty much overlap with the massive boom growth that we have seen in the battery energy storage market in the grid. And I think that now, if you want to go out there and build your battery technology and start producing at mass scale, it's probably going to be a bloodbath, and you need to understand really what you want to do in there, trying to be efficient, trying to find a problem and understand that problem really well, and try to solve that problem, not just come up with a fancy concept that can catch the attention and some funding maybe, but at some point you will find yourself stuck in a scale-up phase because you cannot sustain even your own processes. So do what is efficient.
Yeah, definitely. I think that's great advice, and I think it can probably be applied to every different career, doesn't it? I think if you consistently check back on your original goals and your original plan, and make sure that, as you say, your activity is aligned still with that goal, you can't necessarily go wrong in many cases. I think, as you say, when you lose vision of that and you get maybe lost in the details, that's when you can start making quite costly mistakes. Absolutely. Or go off in the wrong direction maybe without realizing.
Absolutely, yes, because you always need division of powers in every, I think, successful environment. And what I think is that engineers should not be given too much decisional power. I'm an engineer, right? And I don't think that, because engineers will not go to the most efficient way. Because if you give enough resources to an engineer, if you give enough time, they will eventually ask for more resources and for more time. And then there is a cut. Like whenever sustainability is when you put a stop to the flow of resources into an idea, you need to decide whenever it's enough, right? It's never going to be perfect. It's enough. That's important.
Yeah. Goes back to that earlier point of compromise. Sometimes that can be the most effective way, can't it? It might not be the most amazing, complex product in the world, but it achieves the goal that we were looking for it to achieve, and it doesn't bankrupt the company. So totally. That compromise can be good. Yeah, brilliant. Okay, fantastic. Thank you. So question 3 I've got for you then: what can you tell us about application engineering and why it's such a great career?
Yeah, well, it's it's not going to be a great career for everyone. It's been for me so far, and I would redo it 1,000 times. It's also started in a fun way. Maybe if we have a bit more time, I can tell the story why I got into this. But maybe some people don't know exactly what it is, so I will try to maybe debunk it a bit. And you might call it in different ways. In some companies, it's called technical sales, even though it doesn't overlap 100%. Some other companies, you might call it proposals engineering. Also doesn't overlap 100%. But I like to define it in a different way, which is pretty much applicable to a lot of different businesses, regardless of like product or services that they might deal with. And application engineering is pretty much the answer to a question that goes like this: how do customers use our product? And of course, if you like sell an ERP system, or if you sell iPhones, it's going to be different. And sometimes you don't even need application engineering for that. But I work in a product-driven industry, and for us, it's extremely important to understand what is the end use, because that's like as an infinite source of feedbacks and improvement. I believe that most of the improvement that humankind has done, has been through iterations to get like very close feedback with the outcome. And there is no better feedback, no better testing field. Okay, don't quote me too much on that testing field than the market out there. You put a product and you will understand immediately if it works or not. When you design a product, it might be a bit more difficult to understand that. So, and something that you need to be able to do this job. You need to be able to talk with a customer, but you need to be able to have a technical understanding of what you're doing in order to catch that feedback and organize it in a constructive way, give it back to the company and says, look, the market has given this feedback, the competition is doing this. We might need to develop a product that does slightly different things. Or like in 5 years from now, what do customers want? There's no way that if you go to like detailed engineering, all down, buried inside the deeper cellars of an engineering company, you will not have that type of knowledge in there. There is no way. You need a very fast feedback that is on the forefront where you talk with customers. But at the same time, you want to be an engineer that can talk the language of the people that are buried in the cellars. So this link is what gives you a fast iteration and to eventually reach probably competitiveness that you're aiming for. Because otherwise, as I said before, you get stuck into the details, you get stuck into optimizing something that you don't understand. And application engineering means talking with customers, understanding their pain, and trying to translate that into something that our company does. So there's very different languages here. That it's like the customer doesn't come to you and tells you, I need this product, unless you are, again, buying an iPhone, right? So you know the color, you know which model you want. It's fairly easy to deal. But when you work in the energy business, the customer comes and doesn't tell you, I want the transformer. The customer tells you and said, look, I have this problem, right? Yep. How do I solve it, right? And you need to be an engineer for connecting the dots a bit and then being able to give an answer to that, but also you need to be able to speak to a customer, which is not something that really everybody wants to do and not everybody is able to do. So I would say, why is it a fun career? And let's assume that you are someone who is interested in talking with customers. Somebody doesn't want to talk to the people at all during their life or their career, at least their working life. And if you are one of those people that you are curious about the product, the technical aspects of what your company does, but also you are very curious to understand, does this even work? Because this is a question that some people don't ask themselves. If you do a job, like, does it ever happen to you that you ask, like, but is it even needed what I'm doing? Like, how is it used? Right? I'm writing a code. Is it going to work? Is anybody going to test it and use it, or am I doing something useless? Right? It's something that people, I think, at some point tend to ask themselves. So if you feel like your brain works like that, application engineering is a very good career because, first of all, retribution is not bad at all, and it's needed. Companies need application engineers and people that talk the language of the customers while understanding product. This is very valuable. And also, the main aspect that I really like it for is that it gives you this high-level understanding of system approach that your company might produce, pieces for the automotive, let's say axles for the automotive. And it's like the best in doing that. You have a forgery, you have all your metal processing plant, and you do the best axles for vehicles that ever. But then is that enough for you? Like, are you okay knowing that you're executing the production exactly according to the specification? But some people are simply made like me, that is like, I want to understand where those specifications come from and why an axle is made like that and who uses that versus something else. So you start looking above that and to find your reasons, the famous why. To find your reasons, you end up learning a lot that is around that. So you need to be a bit like wanting that, but there are, I think, a lot of engineers that think like that. Where it's not enough to think inside a box, but you want to understand what's around the box, how customers put that box into their house, and what they put inside or outside is out of the scope of your company. But you need to understand that in order to build a good box.
Yeah.
And I think that's the job of the application engineers.
Yeah, like you say, it sounds very interesting, and I suppose it's a good opportunity as well to be at the forefront of maybe innovation. And if you notice a trend in how the product's used, you can obviously translate that technically into improvements, or move into a slightly different market that you maybe didn't anticipate being involved in. I'm sure that happens quite often.
Absolutely, yeah. It's being exactly in this forefront that I was saying. You immediately understand what's happening, market trends. You're in there. You need to be fast. You're in a very fast front line, and then you have the rest of the company that you need to motivate in a certain way or provide indications on how to move forward. But you're there. You're immediately understanding what's happening out there. AI comes up. Next day, it's a potential market. It's a folder on your desktop that you're trying to collect information on. People that are developing products for the AI business, they might know it after 1 year. So if 1 year is too long for you, application engineering is a good career.
Yeah, definitely. Brilliant. Well, Ludovico, thank you very much for your time. I'm sure everybody's really enjoyed your insights there.
Thank you very much.